Now, this gets at some interesting things because what you talk about as fundamental in this theory is not what we talk about as fundamental in current theories of physics. And one of the reasons for that I think is really important because, again, looking at the history of science, we have invented a lot of technology in the short history of science. And every time we invent new technologies, what we call fundamental changes. A good example is atoms, right? So atoms are the things in the periodic table, and they're called atoms because we thought they were indivisible, like the Greek atom. And then we realized they had substructure. And now sort of the most fundamental theories that people want to propose are things like string theory, which is even more fundamental, but currently inaccessible to our technology. We want to define fundamental as the smallest objects in the universe. The problem is, when you're an observer existing in the universe, what you call fundamental changes with your evolutionary history, how much technology you've evolved, how much you can measure. And so a theory of evolution that tells you about where you are in an evolutionary chain cannot have a fixed, finite object as an indivisible object as your fundamental particle. It can't be the fundamental structure of your theory. So assembly theory is a theory of objects. It's kind of funny because I got through a whole physics education without knowing what an object was. And then I started to think about it. And so we define objects as having several features. One is that they're finite and distinguishable. So you see a basketball and a soccer ball in the universe. You don't see a smear of every possible kind of configuration of ball in between. They're finite, distinguishable objects. Objects are breakable. I could decompose your brain into atoms. I can decompose a molecule into atoms. I cannot decompose an electron into anything. It is not an object. It's a limit of your observations. Objects exist more than once. This is a weird feature and probably one of the most unintuitive things, but one of the key features of assembly theory is this idea of copy number, that things that are created by evolution can be produced again. And that the copies of objects matter. So we are not identical objects as humans. So you say, like, I'm not an object in the theory, I don't exist. But actually, if you look at us and you look at our causal history and you look at where we exist in the space of possible, we're nearly identical. You know, we're 1% of our genome is different, right? So you can follow these causal trees building up these objects all the way to the branches, and we're the things that are alive now are just the branches of these trees. Objects are lineages. So this gets to the point about objects existing in time, right? So in order to get to something like you or I, we think, about 4 billion years of evolution has to happen on a planet. And my friend Michael Lockman is really great about saying, when you ask him how old he is, that he's 3.8 billion years old, because some of the information in his body is that old. And even in your lifetime, you're not the same atoms you were when you were born. So what is you? You are the lineage. You are the thing that keeps getting reconstructed. Objects form via selection. I love this website. Sometimes I put it on my slides. That just will generate a human. It's one of the neural networks that's just fun on the internet. But the whole idea is this person does not exist, right? So the space of things that cannot exist is really big. And so you have to ask, why are we the ones that exist? Why are chairs the things that exist that we sit on? Right? Because they were selected out of that possibility space to be finite, distinguishable physical objects. Selection is the mechanism that does that. So this depiction here is an assembly space. It is an assembly space for adenosine, which is a molecule that is used in DNA. And I mentioned that molecules are built out of bonds. So the way we do it is to build the assembly space is you do a joining operation between two elementary building blocks. You build something else. Once that thing is built in the assembly space, you can use it again to build something else and again, and combine it with other features that exist in the causal pathways to build up the object. But when I talk about assembly theory being a theory of objects, this is what we would usually call the object. But in assembly theory, the object is this pathway. It is an informational object extended in time. So adenosine is this pathway. It has all of those features as sort of the compression of this object as a physical object as it is constructed across time. Okay, so I mentioned, thinking about theories of motion, we talk about very specific variables that appear in our abstract theories to describe those objects. And then we give those variables physicality. We talk about these being the real physical features of objects. the things that we assign as physical features of objects are features of our theories, not necessarily the objects. They're features of our descriptions. They have to have a correspondence with the real properties of the objects. Otherwise, we're not doing physics. But in assembly theory, we care a lot about being able to go in the MATLAB and measure things because we actually want to do the experiment to solve the origin of life in the lab using digital chemistry to explore chemical space. And we need to be able to measure when life evolved from a chemical soup in the lab. So we have to measure it. And so the two observable properties that we have in assembly theory, the assembly index, this is how many steps did it take to construct your object. So this is what we mean by assembly time. How many causal operations? What's the minimal set of causal operations to construct that object? And that set of causal operations has very specific properties that are unique to assembly theory. They're not features of other theories of compressibility, although they have some relationship to them. Copy number is the second feature. How many copies of the object do you find? If an object emerges once in the universe, it's not necessarily evidence of selection and causation. It could be random, right? So I said brains don't form randomly because there's too many construction steps. I would never expect to find a brain as a single object. I will always expect to find brains as collections of objects that are related by a causal history that evolve on a planet in bodies. I don't think minds emerge alone. Okay. So I've already covered some of these, but I think they're worth just going through a little bit more slowly. And I think I have a little bit of time here. So one thing I've already said is universe can build new things only if the pieces exist already to build them. So assembly spaces are recursive. So the universe in assembly theory is a recursive universe. Everything that you see is a recursively stacked object. It's built out of things that were built before it. And actually this feature of recursion is so prominent that I would not expect any evolved objects, anything selected to exist in our universe to not have that property. And I have really strong quantitative reasons for saying that I don't, that we're writing in a paper right now. But the structure of these paths is what I described already. So this is not showing molecules now, but this is a graphical representation. So if I have two elements and I stick them together, I can make a line. And if I stick those together and add an extra bond by the process, because I have to stick everything together here, I can make a triangle, but I could also have made a square. And then what follows subsequently is contingent on that prior history. So you can see how the number of ways of building things as you construct objects becomes, vastly untamable in some sense. But the feature of these paths that's important that I want to show you is that one, that they're combinatorial. Right? So you take discrete elements and you stick them together to build things, and they're compositional. That you can only build on things that you've already built. The steps must be timed in operations that are physical and observable. So the assembly index is a physical observable of molecules, and we think it probably is of other objects too, but we have to figure out how to construct the assembly spaces in physically meaningful ways. But this is one example of a assembly pathway. But where it gets interesting is that this sort of idea of building a molecule by taking this sort of minimal path through the space of construction histories for the molecule is actually a feature that's measurable for real molecules. So this is showing a mass spec as you're adding bonds to a molecule and how the fragmentation pattern in a mass spec actually corresponds with the assembly index. So my collaborator, Lee Cronin, is rather ingenious on these things. And so he actually developed assembly theory originally to go in the lab with a mass spec and try to figure out if a system was evolved or not. That was sort of the measurement challenge. And so he took the features of what mass spec measures of molecules to try to construct a way of talking about how evolved the molecule was. And actually, it turns out it's not unique to mass spec. You can measure it with NMR and infrared. So it's not a feature of a mass spec measurement, but assembly index is measurable. Okay, so I've already mentioned this, but I want to state it more concretely. Complex objects can only exist where there are physical systems with the information to construct them. This is how complex objects are products of evolution. They require objects making more complex objects, making more complex objects, making more complex objects. Unless you have that whole stack of causation, you cannot form them because you need all of the informational constraints along those chains to actually produce that specific object out of that huge possibility space of things that could have existed but don't. That's the only way to get the information. So we expect above a assembly threshold, we expect to observe any object unless it was selected to exist. So this is one of the reasons that we're trying to use assembly theory for alien life detection, because we don't care about what molecules they are. All we care is, are they a product of evolution or not? Are they deep enough in this construction history that they're signatures of evolution, that selection had to happen?
If you enjoyed that clip, then the full podcast is out right now. You can click around here Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.